Okay, let's get started. So if you have a homework 5 or a quiz 14, hand those in. And I have a bunch of stuff to hand back. Homework 4, I don't even know what else I have. So quiz 13 and quiz 12. So if you haven't picked those up, please do so. I think we win the award for the most papers interchanged at every class. Yeah. But any questions before we start? Okay, so let's continue the example that we were doing last time, which was this is a PDA, and we want to convert it to a what? Yeah.
CFG?
Yeah, to a CFG. So an equivalent CFG. So what we had to do first to the PDA was several things. We needed to have every transition either push or pop, but not both. And we needed to have one final state. And also with the one final state, have self loops that pop every character off. And then once we made this PDA, then we started to make some rules. So we made an example of type 1 rules, type 2 rules. So to refresh your memory, type 1 rules are always going to be of the form a sub state, comma, the same state going to empty. And the type 2 rules are you have 2 states on the left side, then you have 3 on the right where the first and the last are the same, so the Q0, Q3 are the same on the right side, and the 2 middle states they have to be the same. So if it's Q1, the other one has to be Q1, or if it's Q2, it has to be Q2. So it has to be the same state in the middle, but as long as that is true and the ends match, it's fair game. So are there any other types of rules that we need to make? So if I just stuck with these 2 types of rules, would I ever be able to generate any characters? No, I can't. So what we need to do then is to make a type 3 rule. So let's make a type 3 rule. Let's make that 3 better. There. So what do we need for a type 3 rule? Yeah.
We need a start and a end that goes at 0 and nothing in between.
Almost. So we need something at one point and something else at another point. And I think it has something to do with the transitions in here. So we had this situation where we had a transition that pushed something, and then later we will pop the exact same character. So if this, say, pushes an X, then the other transition must pop X. And assuming it never comes down to the same stack height in the middle. So this is the first time it's coming back, and so it must pop the same character. So let's just say for the first transition we read an A, and the second one we read a B. The first state is P, the last state is Q, the first middle state is R, and the second middle state is S. So what was the rule that we were able to generate by these transitions? So remember, what is my starting state and what is my goal state, no matter what? P and Q. So I am destined to generate a PQ. So one way of going from P to Q is through this route, which is what? What do we see on the first transition? What do we read on the first transition, the pushing? We read an A, good. So then we read an A. Then how do I get from state R to state S? Supposing I know how to get there.
We do A, RS.
A sub RS. Yep. And then I think for the last transition, we read a B. So then in the rule, I'm going to produce a B. So one way to get from P to Q is to do this first transition, do something that gets us to state S, and then finally read a B at the end. So the only way that this will work is if one of the transitions pushes a character and the other transition pops the same character. Okay? So let's find an example of a pair of transitions that have that property here. So pick any two transitions where one pushes something and the other one pops the exact same thing. Any examples? Yeah.
The two transitions that involve the money sign.
Yeah, well, there are three because of the QF one, but let's just say that we want to pick this one right here and this one. So I'm going to reproduce those transitions for our convenience. So Q0 goes to Q, I think it was 1, yeah. So Q1 on epsilon, epsilon goes to $, and the other one goes from Q2 to QF with epsilon $, goes to epsilon. Okay. So what we need to do then is to make the rule. So what is my start state in these two transitions, and what is my destination state? Yeah.
Your start state is Q0, and your destination state is QF.
QF. So what is the variable on the left side of the rule in this case going to be? Someone else. Encourage participation. Yeah. Q0, QF, good. So then the rule that we're going to make is A sub Q0, comma, QF. Because Q0 is the beginning of the push transition, and QF is the end of the pop transition. Okay, so what do we read on the push transition? Well, let's just look at the transition. What do we read on there?
Nothing.
Yeah, we read nothing. So there we go. What are my two interstates here, the ones in the middle? Q1, Q2. So then the variable I'm going to put here is A sub Q1, Q2. And I don't think we read anything on the pop transition. So there we go. So that's a rule that we'll make. Okay, so, and we can actually kind of heuristically see why. So if I want to go from 0 to F, it's the same strings that go from 1 to 2, because the two transitions involving the $, the one that I picked, those don't read anything. So because they don't read anything, whatever takes me from 1 to 2, those are the strings that will be that'll take me from 0 to F. So let's do a pair where we're actually reading something to make it more interesting. So what is a pair of transitions like that where we actually do read something on the transitions? Yeah.
Q1, Q3, and Q3, Q2.
Well, we don't read anything on those transitions.
Oh,
We could pick those, but it's just I want to do an example where we're actually reading something.
sorry, my bad. Q1, Q1.
Yeah, so the self loop on, what's another color? So the self loop on Q1, and I think the self loop on Q2 is also a matching one, because the self loop on Q1 pushes a 0, and the self loop on Q2 pops a 0. Cool. So I want you guys to help me with this one because I'm not sure of my abilities in doing this. So let's see. So I'm going to reproduce those transitions. So Q1 goes to Q1 on 0, epsilon pushing a 0, and was it 2? Yeah, Q2 goes to itself on 1, 0 goes to epsilon. So I want you guys to help me figure out what the rule will be in this case. Yeah.
A Q1, Q2 goes to 0,
0, A,
Q1, Q2,
1. Good. Exactly. Because Q1 and Q2 are the begin and the end states because it's always the begin and the end in this case. Then on the push transition, we read a 0. The intermediate states are again Q1, Q2, so that's why we have that on the right side, and then a 1 on the end for the pop transition. Okay? So that's another example of a type 3 rule. Any questions about these types of rules that we have made? So what can we say now? Well, did we have to think about the structure of the PDA in order to make these rules? Well, let's see. Does type 1, did we have to look at the PDA in order to figure out what the type 1 rules are, other than what the states are? No, I just make one of those rules for each of the states. No matter what the states are, I just make one for each. What about the type 2 rules? Did we have to think any clever thoughts about what the PDA looks like or which rules make sense or whatever? Or did we just blast through making a whole bunch of rules? So you know how, one way that you could like really mess with your instructor? So whenever they ask a yes/no question, answer maybe. Okay, so this one's a definite maybe. No, I'm kidding. So in making the type 2 rules, did we have to think about which rules we're going to add? I don't think so, because again, it's just what the 2 states on the left side are the bookends of the variables on the right side, and the ones in the middle on the right side could be anything as long as they're the same. So I don't have to think about the structure of the PDA anymore. Cool. Well, what about the type 3 rules? Surely they look at the structure of the PDA. But here's the thing. All that we're doing is looking at matching pairs of transitions. I don't care what the rest of the PDA looks like, because look at what we were doing here. We were looking at a pair of transitions in both cases, and we don't even care what the rest of the PDA looks like. We just look at this pair. So all that we really need to do here is just look at all pairs of transitions, see if they're compatible, meaning that one pushes something and the other one pops the exact same thing. And if they match, then we can just blast through and make a rule like this. So this tells us then a really important result, that every PDA can be converted into an equivalent CFG. Any questions about that? Great. So now let's move to a slightly different topic, but kind of how we actually did it with regular languages. So we talked about NFAs and DFAs, and then we did regexes, and then we did what? So what was the big proving results section that we did after regexes? The two words that strike fear into the hearts of all computer science students. The pumping lemma. Round 2. Okay, so let's see. So maybe all languages are context-free. That might be true. Maybe no matter which language you design, it's always context-free. We can always make a grammar for it. Or maybe not. So, and we asked the similar question with regular languages. So the question to answer now is every language a context-free language? So how did we show that, how did the pumping lemma for regular languages go? To refresh your memory, what we did was, we supposed that we have a regular language on our hands, then we fed a long enough string, so that states would repeat, and then we could just repeat that middle part as much as we want, and then go to a final state. So could we do a similar type thing with PDAs? Because it's also a state-based machine. Could we just say, feed a long enough string so that it repeats, and then we can just repeat that part as much as we want? Could we do that with PDAs in the same way we did with DFAs? It seems tempting, but there's a big issue that we'll run into. So suppose that we have a situation like this. So let's just say that this is some state right here, and let's just say for sake of argument that it has a transition reading an A, popping an X, pushing a B, going to somewhere else, and then it has another transition that involves reading an A, popping a Y, and pushing a B. It doesn't matter what we push. And let's just say that we have a looping type situation here. What could happen? Well, let's see. In the DFA situation, if I go to some state and I read the same character, I'm going to always do the same thing, regardless of what I've seen before. Well, PDAs are non-deterministic, but that's not the issue here. Well, suppose that we end up at I'm going to color it red here. Suppose that we end up at this red state right here, and we go down the popping Y loop. So we take the transition that pops the Y, and then we come back. And suppose that the next thing I'm going to read is an A. Am I guaranteed to do that same transition? That pops. Why? Why not?
Why might not be on the top of the stack?
Might not be on the top of the stack anymore. So that seems like a big issue. And it seems like it's such a big issue that we're going to try to avoid it. Maybe we can do some kind of repetition with maybe a CFG, for example. So could we have some type of repetition in something else with a CFG? So let's see. Could we get a repetition, whatever that means, in a CFG? Because that's really our only shot. PDAs seem like seem kind of irreparable in this respect, at least. Maybe it's possible with the CFG because the grammar is context-free, remember? So if I apply a rule to a variable, then it doesn't matter what's on either side of that variable. I can just replace the variable however I like. So maybe it's a better idea to work with CFGs instead of PDAs, because PDAs are, it depends on what's on top of the stack now. So could we get a repetition in a CFG? Well, we again run into an issue because what could appear on the right side of any rule in a context-free grammar? In any context-free grammar. What can appear on the right side? Anything. So again, this seems like an issue that anything can appear on the right side, and so whatever repetition we would want to get, well, the right-hand side could be quite complicated, and so it might be really hard to find a repetition. Is there a simpler form of CFGs we've talked about? Yeah, CNF. What if we have a CFG in CNF? Could we get some type of repetition? Well, let's actually try to figure that out. Well, what could the repetition possibly be? Well, in the grammar in CNF, what has to be true of the derivation until the very end? So not at the very end, but all the way up to the very end.
They have to be two variables?
With two variables, but then I apply another rule to get variables upon variables. Yeah. So the derivation for most of its life is just variables. So maybe we can get a repetition in variables. Maybe that's true. Maybe we can't. Maybe we can. So one of the things that you should always take from this class is don't be afraid to try something, even if it ends up not working. So, and it turns out that this will work. So let's look at a derivation in a context-free grammar in CNF. But is there another way that we can view a derivation? We've actually talked about this before, and it's something called a parse tree. So remember what a parse tree is. So let's actually talk about parse trees. And maybe my mind is fuzzy today. Maybe did we talk about parse trees? Oh, okay. Okay. So let's see. So suppose that we have a grammar like this, 0s1 or empty, and let's just say that a derivation is 0s1 goes to 00, s1, 1 goes to 0011. Okay, so this is just an example. So how would you form something called the parse tree from this? So what you do is the top of the tree is the start variable, and what you're going to do is you're going to form a tree going down where at each point you're applying the rule. So the first rule we apply is S goes to 0, S1. So the children of this root node, if you like, has 3 children, which are going to be 0, S, and 1. And the variable, we applied 0, S1 again. So this middle node right here, which is again S, also has 3 children. Which I'm going to, again, call 0, S1. And then what was the rule at the very end that we applied? Yeah, it goes to empty. So here in this tree, what I'm going to do is this S is going to have a 1 leaf node now, which is going to be empty. Okay? So a parse tree is basically just a top-down view of what the derivation actually is. But notice something interesting. Read the leaves of the tree going from left to right. What do you see? So the nodes at the very bottom.
It is the final string.
It's the string that we made. So 0, 0, empty, 1, 1, which is exactly the string that we made. Cool. So let's see. So I'm not going to prove it here, but remember the concept of leftmost derivation? So you have a derivation, you always work with the leftmost variable first. So if you have a leftmost derivation, you always will have a parse tree and vice versa. So the number of leftmost derivations is exactly the same as the number of parse trees that you could generate here. And the basic idea is if you have a leftmost derivation, well, you just expand the tree in the order that you applied the rules. And for the other direction, you basically do the same thing in reverse. So here, remember that if you have a derivation, you always have a leftmost one. So if we want to talk about a derivation in a grammar, I might as well just talk about parse trees because they're exactly the same. So if I have a derivation, I can always make a parse tree out of it and vice versa. Cool. So let's see. Well, if we're trying to get a repetition of variables in a context-free grammar in CNF, well, let's look at what happens to the parse tree. So let's look at the parse tree. So here is a parse tree of a CFG in CNF. And it may look a little weird, but we're going to talk about it. And no, this class is not a pyramid scheme, even though it kind of looks like one. Any of you want swampland in Florida? No, I'm kidding. So let's see. Well, what is always at the top of a parse tree? The start variable. Good. So the start variable's here. And what do we know if we just read the leaves at the bottom of the tree left to right? What do we see?
The final output.
The final string that we have derived, yeah. So if I read from left to right, I have the string W1, W2, W3, all the way to Wn, all the way across. So the interesting question here is, what is in the middle of the tree? Well, let's just say the tree is sufficiently big. Well, what is near the top right under the variable s? Supposing that the string is long enough. Well, what?
Two variables.
Two variables. So there's a variable here, let's just call it A, for example, a variable B here. And what's true about those variables right under them? So right under these two variables, what's also true?
And they also must have variables.
They also go to two variables. And each one of these has two children, etc. What do we have on our hands? What kind of tree is this called? A binary tree. So by restricting the form of the CFG to be in CNF, which we can always do, every single parse tree must be a binary tree, except for the very end, where what happens at the very bottom of the tree, where we have the terminals at the very bottom, but what about one level up from the very bottom of the tree? So how did each one of those terminals get made in this grammar? With one. So at the very bottom, these leaves are attached with one variable. So it's not exactly a binary tree because there are some nodes with one child instead of two, but if we take all of the leaves off of the tree, then it is a binary tree. Cool. Is this a complete binary tree necessarily? So is it always like completely filled out in every layer? No, that's not necessarily true. It could be that one side of it makes a terminal early and another side is really deep. That could be true. But the thing is, the tree is always a binary tree if we take off the leaves off the bottom. Any questions about that? So let's explore this a little bit. So let's see. If I make the string at the bottom, the string we want to derive, if I make that longer and longer and longer, what has to happen to the tree, to the parse tree?
Its height has to go up.
It has to eventually go up. Why? But suppose that we have a complete binary tree on our hands. So that means that it's completely filled out. But if I add one more character to the string, the height has to go up because it's a binary tree. So if I make the string longer and longer and longer, the height has to grow at some point. So this tells us that if W becomes longer, eventually the tree becomes taller. And that's kind of like a pigeonhole principle type argument there. Because if you make the string longer and longer, well, the tree can't stay the same height after the string is sufficiently big, because the complete binary tree only has a certain number of nodes it can have. So let's see. Well, if we want to repeat variables, suppose that we have, let's just say 10 variables for now. If I make the height so big that there are at least 11 variables on the top to the bottom, what does that tell us? So, well, go ahead.
So did you say there's 11 variables?
So yeah, so this is what I mean. Let me actually draw it for you. So here's our picture again. S is at the top. And what I'm going to do here is I'm going to look at some way to get from the top to the bottom. So and I want this, and I'll explain why. I want this top to bottom path to be the longest root to leaf path. There are multiple, I don't care which one. As long as I have the longest one, that's all I care about. So let's just say that, just for sake of argument, that V has 10 variables. So there are 10 variables in the grammar. And this height right here is at least 11 from the top to the bottom. What has to happen?
One of the variables has to repeat.
One of the variables has to repeat. And that's the same argument as when we did it for DFAs. If we had P states and I fed a string of length P in there, we saw at least P plus 1 states, and therefore one of them must have repeated. Same idea here. If we have a certain number of variables and the height is at least, strictly larger than that number, then that means some variable must have repeated. Can the start variable be the variable that repeats? No, because it can't appear on the right-hand side of the rule. Isn't it amazing how you thought, well, Chomsky normal form is just this arbitrary thing Ryan's assigning us, but it has all of these amazing properties. Isn't that cool? So I think it's cool, at least. Okay. So what can we do with this? So let's make another picture and make it a little larger. I'm drawing all these pyramids for you, and I swear it's not a pyramid screen. Okay. So what can we do? So let's make the tree so big that a variable has to repeat. So let's just say that this is the tree. And S is at the top again. Well, some variable repeated. I don't know necessarily where it is, but let's just say here's the path, the longest path from the top to the bottom. And let's say that a variable A repeats. And so let's just say that's the first one. And right here is the second one. Actually, I'm going to move the text over. There, that's better. Okay. Well, let's see what happens. Could the variable A make the empty string? No. Why not? Right, we got rid of that, and A is not the start variable because the start variable can't repeat. So that tells us that this variable A must make something of the string. Must make something of the string. So let's actually look at the parse tree that these two variables, or at least the occurrences of them, let's look at the parse trees that they themselves make. Not the one that S makes, but the ones that each occurrence of A makes. So let's look at the parse tree that each of these occurrences of A make. Well, the second occurrence is lower than the first one, so it can't make the whole thing that the first A makes, but it makes something of the string. So what I'm going to do is I'm going to name these parts of the string. So the string that corresponds to this first part, I'm going to call U. This next one, I'm going to call V. The middle one, I'm going to call X. Fourth one is Y. And the last one, Z. Okay? Do we have time? Maybe. Okay, so let's see. So we have 5 parts right here. Well, what can we notice here? So what do we notice about these 2 variables that I'm circling? What do we notice about them? Don't think too hard. They're the same. So here's something crazy that you may want to do. Crazy Ryan goes again. So could I take the big parse tree for the one for the first A? Let me actually just highlight it. So can I take this green parse tree right here? Could I copy and paste it down to where the second A is? So let me draw it for you. Hopefully I can copy this. So here's what I'm proposing to do. What I'm proposing to do is I'm gonna copy this green parse tree down to where the second A is. But because I copied the green parse tree down, that means we get another occurrence of A. Because the green one has 2 occurrences of A, so we get another occurrence of A because I copied it. So let's just say it's here again. And the little parse tree that it makes is down here. Question for you guys. What do those 3 parts in the middle for the copied parse tree represent?
Is it VX, Y?
It's Vx and Y. Exactly. So this part's V again because I'm just copying it from the top one. So then this part's the X part. And here's the Y part. Because again, it's just copied. So because we made a parse tree for the string, could the grammar make that string? Yeah, because every parse tree corresponds to a derivation, which means the grammar can make it. So what we had before was U, V, X, Y, Z is in the language, because that's the original string. Well, if we read off of the leaves of this parse tree, what do we get? If we just read from left to right, what do we get? So we have to go from the very left. So U, V, and then what's next? Going from left to right. Another V, right. So we have U, V, V, and then X, and then Y, Y, Z. Which I'm going to abbreviate to U, V squared, X, Y squared, Z. And because we made a parse tree for it, it's also in the language. You guys getting flashbacks?
Yes.
Okay. What if could I do this copying and pasting thing as many times as I want? Okay, cool. So we can get it as many times as we want. What if I did the opposite? What if I took the little parse tree for the second A and just copied it up to where the first one is. So we get a shorter parse tree in some sense. Could I do that too? And that would eliminate a v and a y on both sides. So that tells us that u, v to the I, x, y to the I, z is in L for all I at least 0. So instead of having 3 pieces where we pump 1 piece, we're going to have 5 pieces where we pump 2 of them. The same amount. So notice that the exponent for the v and the y part is the same. So if I put another copy of v in, then I have to put another copy of y in. I can't independently choose the exponent here. Any questions about that? Okay. Well, let's see. What else can we say about this? Well, yeah, so what can we say about this? Well, let's look at an extreme case of what could happen. So let's just say that we have the derivation here. Here's A, and let's say that A is immediately a child of A. So the second occurrence of A is right after the first one, just as an example. And then maybe some other variables on the other side. Well, let's see. Well, if we expand this out, then what happens? We get something that looks kind of like this. So something like that. I'll zoom into this. So this top A is going to make whatever the A below it makes, along with whatever the B below it makes. So can the B variable make the empty string? No. Why? Only the start variable, and B is not the start variable. So that means that the top A is going to make at least one more character than the second A is going to make. Because even if the second A aligns with the top A, like it is doing here, the other side, whatever the other variable is going to make, it's got to make at least one character. So that tells us that one side of this little parse tree right here is going to have something that the other A doesn't have. Could I flip this picture around so that the A is on the other side? The second occurrence of A is on the other side? Yeah, I certainly could. So, well, let's see. What is the B part making here? Well, the B part is making, if we look at our picture, is making either the V part or the Y part, because that's one of the two sides it corresponds to. So one of those two, the V or the Y part, must not be empty. It could be that the V part is empty, but the Y part can't be empty, if that's the case. So one of the two must be non-empty. So this tells us that the length, so I'm going to phrase it in a different way. This tells us that the length of Vy is at least 1. Because if both of them were empty, then the length of this, when they're both empty, is 0. But as long as one of them is not empty, then the length must be at least 1. So another way to write it is the length of Vy is at least 1, or Vy is not empty. That's another way to write it too. And I think we're out of time, so I'll see you in lab today.